All right, welcome back. Today we are going to talk about thermal imaging and how to use thermal imaging in a photogrammetry context within Metashape. So, thermal imagers have become increasingly common on drones. We're seeing them on drones of all different price points right now. And I mean, let's be honest, thermal imaging is really cool. And the fact that we might be able to take thermal images and create larger thermal orthomosaics of like whole landscape just is kind of mind-blowing, really. So before we get into Metashape and working with thermal imagery in Metashape, there's a couple of aspects that I wanted to cover. Thermal imagery is just a little bit different than the RGB or multispectral imagery that we've worked with so far. So we just need to understand kind of what it is about these images that makes them unique and how they were collected. So the first thing we want to look at is there are generally two types of thermal imaging sensors, or TIR sensors, on drones. You have inexpensive sensors that are not radiometrically calibrated, and then you have more expensive sensors that are radiometrically calibrated, meaning that there's a relationship defined between the thermal signature or thermal value of each pixel and a temperature. And you can technically do photogrammetry with either set, but there's a problem with the non-radiometrically calibrated images that we've seen. And so on this slide, I've got two sets of photos. These were both taken from a drone that was flying over a beaver pond, and we were looking at water temperature within the beaver pond. And the top set of images is from an Autel Evo 2 Duo 640. I don't know, there's all sorts of letters and numbers in there, but it was a sensor that was not radiometrically calibrated. So it was the less expensive version of this drone and sensor. And you can see, if we start on the picture on the top left, right, when that picture is taken, the sensor or the sort of camera assigns the full range of colors available in that color ramp for that photo. So the coldest pixel in that photo is going to get the darkest color, the coldest color, so that would be like a dark blue. And the warmest pixel in that photo is going to get the hottest color, or that sort of pink or white color. And then when the drone moves over and takes the next photo in the sequence, it's going to apply that same color ramp again. So it's going to give the coldest pixel the coldest color, the hottest pixel the hottest color. And the effect of this, as we move across the set of images, as we sort of fly across this beaver pond, is that the temperature of the water appears to change. It appears to get warmer as we move across. And you can imagine that from in photogrammetry of creating an orthomosaic, that's not a desirable property to have. Contrast that to a flight over the same beaver pond with the radiometrically calibrated version of that camera and that drone. You can see then, as we move across the beaver pond, it's one color ramp that's being applied to the temperature range, not to each individual photo. So the water temperatures appear to stay the same as we move across the beaver pond. So the take-home message here is that if we're want to do photogrammetry with our thermal images, it's probably pretty important to have radiometrically calibrated sensors so that we know we're actually measuring temperatures consistently as the drone moves across the landscape. Okay, next thing we want to look at is how we're actually storing these photos. So I have a file browser up here, Windows Explorer window open, and you can see all the photos that we have here, and they look like they're stored as JPEGs. And in fact, if I even come in and double click on one of these, open it in the Windows photo app, right, looks just like a normal photo. The color ramp is applied to this photo, it's assigned, and it's not apparent right away like where my temperature data actually is for this photo. A common format for storing photos for thermal data is this RJPEG, or a radiometric JPEG file. So they will look like regular JPEGs. If I even go into the image properties, look at that, I'm not going to see anything unusual there. But if I come over to QGIS and bring the photo in there, now I'm seeing a different representation of this photo. So what's happening here is that the ArcJPEG format has the 3 RGB bands of a normal JPEG, plus it has a 4th band that has the thermal data in it, right, or the temperature values. So if I grab my identify tool and I start clicking on pixels here, you can see over here, here's my actual digital number band values. Okay, and these are directly related to temperature values. We'll look kind of later on how we convert these to temperature values. Okay, so the take home here is that I need to use an app that can understand and read these RJPEG files. Luckily, Metashape can do that, but there's going to be a little wrinkle on how we bring them into Metashape so that it recognizes them as these thermal image files and allows us to access the actual temperature data from those. Okay, so with that out of the way, let's come over to Metashape. I have a new project here. We're going to add our thermal images here. Okay, now this is the wrinkle that I was talking about. So it's asking how we want these things to be brought in. It's recognizing that there are 2 layers for each of these photos. So it can either bring them in as single cameras, which each photo would count twice, once for the RGB version, once for the thermal version. I could create a separate chunk for each one, which I don't really want to do, but that gives us this multi-camera system option, which is the same as we would get if we were bringing multispectral data in. And this is going to basically like attach both layers together as a single photo. So I'm going to choose this multi-camera system here, hit OK. All right, I've got my points on the map. Those look pretty good. Here's my list of photos. I've just changed this to look at it as a list rather than to look at the individual photos. I can, if I double click on one of these photos, then right here's my RGB representation, but notice on the side now I have a new pane that shows me both layers. And so if I click on this guy, you know, the sort of contrast of this image is not really great, but this is basically the same thing that we were seeing over in QGIS. So I could toggle back and forth between these. The thing to know here is that it's brought both the RGB version and the temperature data in, assigned them as 2 layers to the same image. Okay. I could go ahead and align these photos from here. In fact, let's actually do that. We'll just do a quick alignment on them, choose medium accuracy, leave everything else the same. This is going to run probably a lot faster than you're used to with Metashape stuff, because these thermal images are pretty low resolution compared to what we're used to dealing with RGB photos. So yeah, it should be pretty quick. I'll go ahead and pause, let this finish running, and then we'll come back and take a look at it. All right, so when the alignment was done, I got that dreaded "some photos failed to align" message that you get in Metashape sometimes when you have issues with images and image overlap. And my experience is that this is not uncommon with thermal images. And I think there's a couple things going on. You know, one is that these images have a small footprint. They're sort of low resolution photos. They don't cover a large area on the ground. Thermal photos that are shot at the same time as RGB photos, you have to take special care to make sure that you're getting the correct overlap with your thermal photos. But even then, a lot of times the camera information either doesn't get read in off of the image header files, or the Metashape just for some reason has a tough time estimating the camera interior orientation properties like focal length. luckily with this, there's you know, kind of an easy solution to this. So I can come over to the details, and then, okay, so I've sorted this by what photos are aligned and which ones aren't. So photos that are aligned have a check mark, and then I can just sort of select all the ones that didn't align here. Okay, we can see them selected on the map here as the dots. And then I can just right click down here in the photo tray and choose align selected cameras, and generally this actually, yeah, there you go. So generally does a pretty good job of kind of picking up the extra photos that we didn't align. Sometimes to get that to work, I have to, you know, grab a set of photos right adjacent to ones that are aligned, align those, and then kind of like build my way out from there. But once you've got, if you have to do that and align cameras individually to get a complete set, then once you're done, you should flip over here to the reference pane and do an optimization on that, just to kind of clean things up a little bit. Okay. I'm going to reset the alignment on all of these. Okay, and we're going to sort of start over here, but instead I'm going to come into Tools and Camera Calibration, and notice here that I don't have any properties set for my camera, so I'm just going to set the focal length here manually for both cameras. Now there's two cameras listed in here because one of them is for the RGB photos, and the second one is for the thermal sort of band that goes with those as well. And 13 millimeters is the published focal length for this sensor. It's a FLIR boson sensor that's in the drone. Okay, so I'm going to go ahead and hit OK there, and then I'll come back up and align my photos here, and hopefully we'll get everything to align the first time. So if you're working through the lab document itself, you know, no need to align them first without setting the focal length. I just wanted to show that to sort of demonstrate what happens in that case. But yeah, just go ahead and set your focal length and then align your cameras accordingly. So I'll pause here and then we'll come back once they're aligned and take the next step together. All right, happy day. We got all of our photos to align. Everything looks pretty good here. I do have ground control for this area. This set of photos was actually a small subset of a much larger area that we flew, so there's not a ton of ground control in this area, and I think for the purposes of this lab, we don't need to really worry too much about it. However, if you were going to create products that you were going to use in you know, in the real world, so to speak, then yeah, you'd want to go through and do your ground control, and that process would look just the same as it does when we do it for RGB photos. So from here, we're going to go ahead and build the rest of our products. Normally for RGB or multispectral data, we would build a dense point cloud, and then build a DEM from that, and then our orthomosaic. And the reason I tend to go through those steps in particular is because I think each of those products is useful in its own right. The thermal dense point clouds, I'm not entirely sure how useful they are, so we can actually skip that step and just go right to building our DEM. So if we come up here to workflow and build DEM, again, always make sure you're building raster products in projected coordinate systems. Okay, now for our source data, we don't have a dense point cloud to use, but we will go ahead and use the depth maps. Now, what Metashape would do is build the depth maps in order to make the dense point cloud that we would normally use to make the DEM, right? So we're going to have Metashape go ahead and build the depth maps, and then just skip the whole like dense point cloud sort of generation as a product, and then we'll just create the DEM from the depth maps. Okay, so it's just a bit of a shortcut step. It's going to you know, result in us getting a DEM without having to get a point cloud first. So it just saves us a step. We can leave all these other options the same here, or leave them as defaults, and then go ahead and hit OK. Now this, whoops, it wants me to save the project first, so let's go ahead and do that. Come in here, we'll call it Thermal Lab 2, because I tested this whole thing out with Thermal Lab 1 first. So okay, there we go. Now let's come in, build our DEM with depth maps. Medium quality is okay. We'll hit OK. This is going to take longer than what we're used to seeing with building a DEM, because we're basically going through part of the process of building the dense cloud first. So I'm going to pause here, and then we'll come back and look at the next step. All right, that's done. So we can come over here now and look at our DEM. Yeah, I mean, it's DEM, right? It's coarse resolution imagery, so it'll serve the purposes of creating our orthomosaic. So next step is go to workflow, build orthomosaic. I think we can pretty much leave all of these just as they are, and go ahead and hit OK. It'll take a second to run this, so again, we'll pause here and pick up after it's done. All right, so that's finished running. We can come over here now and look at our orthomosaic, and yeah, that's pretty cool, right? Looks like everything came together pretty well. So there's a thermal orthomosaic of our stream system and all these beaver dam complexes here. Now, while this is pretty cool to look at, it's showing us the RGB representation of the thermal data and not the actual temperature values. Now, I could export this from Metashape, open it in QGIS or in ArcPro or something else, and find those thermal temperature values, but I want to try to get to them from within Metashape here. So we're going to do that with a raster transform. So this is similar to what we did when we built NDVI layers with multispectral data. So we're going to come over here to Tools and Set Raster Transform, and we're going to build an expression. So the values that we saw for the thermal band, which is this band 4, okay, there's a sort of published expression for how to convert those to temperature values, and what they actually are is a temperature value in Kelvin times 100, and so to get that in degrees Celsius, we just need to implement a sort of a basic formula, right? So we're going to do band 4 times 0.0105 minus 273.15, because that's the offset between Kelvin and Celsius. So the published equation for this would be to multiply the pixel values times 0.01. We actually had temperature loggers along this stream, and when we did this, we actually found we got closer matches to our in-stream temperature loggers if we modified this equation a little bit. So that's how I got the 0.0105 value here. And again, that's just a rough ballpark. We could probably do a better job just actually doing like a regression between the two, or plotting those out. But this will serve for right now. However, a take home for this is if you really need temperature values, it's a good idea to have some temperature loggers or a temperature probe that you can shoot a bunch of photos or a bunch of temperatures to match up to your photos to actually construct your own adjustment, your own equation here. Okay, so I'm going to hit apply here, and now watch what happens to the map in the background when I do. Okay, it basically turned, well, it did turn the whole thing red, right, except for a couple little pixels down here at the bottom. So what's going on here is that it has applied the raster transform here to this color ramp that ranges in value from 0 to 1. And that's just not super helpful for us because our values extend beyond 0 to 1, right? So we need to update the palette here. And so we're going to first click this update button, the little recycle or refresh button here. And that's going to show me the histogram of the full values, right? So things are going from about, 5 to 7 degrees all the way up to 40 degrees, okay? And then if I click the auto button here, it's going to reassign this color ramp to that range. All right. Now if I hit apply, you can see I've got a sort of color representation of that area. You can play around with this. You can pick different sort of preset color ramps that Metashape has. I think they're pretty limited, actually. Just do whatever you want here. I don't actually like this this sort of 5-color ramp, so I'm just going to get rid of these colors, and we'll just do it a blue, yellow, red color ramp. And that looks a little bit more interesting to me. But again, there's no right answer here. Just play with that and to get it whatever you need. Okay. Now the other interesting thing here to note is once we've applied the color ramp, first of all, we're looking at the actual temperature values now, not the RGB representation of it. But second is, as I move my mouse over this area, check out sort of down here in the bottom right-hand corner, this index value. As I move around to different spots, that index value then should, it is our calculated temperature that we have for that raster transformation, okay? Which is kind of cool because now we can actually see, it's like the identify tool in a GIS package, right? We can see the actual temperature values that we have across our image. Okay, and then if you want to get back to your RGB representation, you can just turn the raster transformation off. Okay, so you can just toggle that back and forth as you need to. All right, so that's it for this tutorial. Again, thermal imaging is super cool. I think there's a lot of potential for it in natural resource and agriculture applications to create temperature maps, temperature orthomosaics over large areas. I think we're going to see a lot more of this kind of imagery in the future and learn a lot more about sort of best ways to collect these data and best ways to process and use them. But hopefully this will get us started in that process. All right, thanks.